Swayam Prabha. Digital India. Educated India.
We have also discussed input and output impedance. Okay, input and output impedance of the associated with amplifier. Okay, we have seen that if I have an input signal, say Vs, okay, and Rs is the resistance of that input signal which you want to amplify, okay, and Rin is the impedance or resistance associated with the amplifier, and the amplified signal, if this is V, okay, and this is R out and R load, okay. So then this R in ideally tends to infinity, okay, and R out should be tends to 0, ideal case, okay. So this part we have learned yesterday. We have also learned couple of things. For example, what is this input and output impedance when we look from 3 different terminal of BJT. When we look from base side, of course the emitter is AC grounded, then we will see R pi, okay. When we look from collector side, okay, this resistance is usually R naught if there is no RC there, okay. If there is RC, then it will be R naught parallel RC. And when we look from emitter side, okay, without any early effect consideration, then this will be 1 by GM, okay. So these are very important, and you will see we often will use them directly, okay. So this part we have learned in the last class. We have also learned there are different topology, amplifier topology possible. Out of these we will mainly concentrate on the common emitter topology, okay, for the discussion of the amplifier, okay. Now if we just now concentrate on the core BJT rather than with all sorts of biasing, for example voltage divider biasing and all that, let's just concentrate on a simple BJT common emitter amplifier circuit without bothering about the biasing, and later on we can add biasing and see what are the changes that make and all that, okay. But we will implicitly assume that it is in the forward active mode. So let's draw a very simple common emitter BJT which has V in that we like to amplify, okay, and this emitter is grounded. That is why this emitter is basically between output and input. It appears like it is in common between output and input, and it is grounded. That is why it is common between input and output, and we call it common emitter circuit, okay. So so you see, if we increase this V in by delta V, okay, if we increase V in by delta V, then the current here will of course increase by GM delta V, right, because GM, you remember, is the trans conductance, which is IC, del IC over del VBE. Okay, so if you increase this delta V here, corresponding current increase in the collector side will be GM delta V. Okay, now we can basically draw the small small signal model of this circuit, uh, which is GM V pi. Here that is the current source in the collector side. Okay, the emitter is grounded, this is V in, this is R pi, and this is your V pi. Okay, there is a resistance RC, which is again grounded, because we basically this RC is basically AC grounded. Okay, and we have output V out here, sorry, right. Now we can find out, so this voltage, this current here will be minus V out over RC. The reason it will have a negative sign, because you see the current is flowing like this, GM V pi is flowing like this, whereas V out polarity we are assuming this. Okay, so current direction and voltage direction we are assuming. If you look carefully, there will be a negative sign. So we can write these V out over RC is equal to GM V pi, and your V pi is nothing but your V in. Okay, so we can write V out over RC, okay, is equal to GM V in, right. Sorry about this. So so we can write V out over V in is equal to your gain is nothing but GM multiplied by RC. So this is the gain of this simple common emitter amplifier circuit, which has a resistance RC between the collector and the DC voltage, and we have grounded that RC because RC is AC grounded. Okay, because we have shorted that DC voltage, because we are doing AC analysis. Now, couple of things we can infer. From this equation. One of the thing is, we mentioned it before, this output and input signal is 180° out of phase. Okay, that is why this negative sign is coming. Okay, this is because if you increase the output voltage, if you increase the input voltage, output voltage will increase, but in the opposite direction, because the VCE voltage will decrease. Okay, I mean the magnitude will increase, but it will have the opposite polarity. Okay, so it is 180° out of phase. Another point to be noted is AV increases if we increase RC. Okay, third point I would like to make, AV will increase if we increase GM. Okay, by increasing GM I mean because you see GM is basically ICQ over VT. Remember, yesterday we calculated GM is equal to ICQ over VT. So if that is the case, then you see by increasing GM, we are the way we can increase GM by increasing ICQ. Okay, so in both point 2 and point 3, what we ultimately it suggests whether we increase RC or we increase ICQ to increase the gain. You see the voltage drop across RC. Okay, that is the voltage drop across RC going to increase. Okay, In both the cases, whether you will increase RC or you increase ICQ, voltage drop across RC is going to increase. Okay. If we just jot down whatever we have discussed so far, if we just bother about the amplitude, okay, we can write so that's RC over VT. So that's basically VRC, that is the voltage drop across RC over your gain. Okay, but you can't really increase your ICQ or RC infinitely. You can't do that, right? Because which that will be limited. That will be limited your by your VCC. So VCC will always be more than VRC. Will always be more than that of the voltage drop across your RC. Okay, so we can basically write this is this gain will be limited. This gain will be limited by VCC over VT. Okay, we can fine tune this inequality bit more because you see RC, I mean the voltage across RC will not go all the way to VCC. Okay, in fact we have to keep this transistor in the forward active mode. So we have to keep in mind that CB, these junctions should be reverse bias. Okay, so we can fine tune this inequality bit further. Let's for the time being assume that so this is your okay, so this voltage here and this voltage here, so this is your VCB. So VCB has to be reverse bias so that this remains in the forward active mode. Okay, let's consider let's think it little bit aggressively and think that say VCE is equal to VBE. Okay, let's think little bit aggressively. If say this is the case, okay, that's basically like kind of you are going to the edge of saturation. Okay, then we can fine tune this above inequality as so gain will be limited by this. Okay, so this is what I mentioned in the last class, that the gain will have I mean the VCC or this supply voltage has influence on the gain, because this supply voltage will dictate the forward active condition of the transistor. Okay, we can do a small problem. Let's assume that VCC is equal to 1.8 volt for a common emitter amplifier circuit. Okay, the power of the BJT power budget is say 1 milliwatt. Okay, let's assume that VB equal to 800 millivolt. Okay, and say find out RC. So this is like a design problem. Find out RC so that it can amplify the input signal of 2 millivolt peak to peak. Okay, 2 millivolt peak to peak it can amplify. Okay, now you see, if I consider this above inequality, it will be easier for me to find out RC. Okay, so say VCC is equal to VCC is equal VCC minus uh, VCC minus ICQ RC, okay, nearly equal to VBE, say, okay, because that is what we have assumed here. Okay, from that assumption we are writing this, okay, and if VBE is 8, okay, RC will be should be less than uh, IC, okay, and you can find out IC because because P is the power budget of this circuit is 1 milliwatt, so you can find out IC by taking VCC multiplied by ICQ is equal to 1 milliwatt, and that IC or ICQ will be 0.556 according to my solution, 0.556 milliamp, okay. So you can find RC less than 1.8 kilo. So if you arrange your simple amplifier, common emitter amplifier circuit in this fashion, okay, RC you have to choose less than 1.8 kilo so that the circuit remains just in forward active mode, okay. So we can find the gain straight away, okay. What we have assumed so far, that this is like 800 millivolt, okay, and we have assumed peak to peak 2 millivolt. Here we have assumed that this is again at 800 millivolt because we said like VCE we are assuming equal to VBE, and this will have like this is less than 1.8 kilo ohm and this is 1.8 volt, okay, and this you can find the gain, okay, gain will be 38.5. So your output peak to peak, which is basically at the edge of saturation, is close to around 77 millivolts and so on, okay. The only thing I would like to point out here is your VCC has an important role to play to find out your maximum gain, okay, which you can achieve. Beyond that you will have it will go to the saturation and distortion will occur and all that. Again, you can find in this simple circuit the corresponding input and output resistance that I have discussed already in the last class. Let me reiterate once more. So we can so this is your RC and this is the ground, this is the R-pi. So we have added a test voltage Vx, okay, and so your Rin is basically over Ix, and that is R-pi, okay, and we know R-pi is beta over Gm, okay. In other words, as I mentioned to you before in the last class, that if you increase your ICQ, your R-pi is going to decrease, okay, and you remember your ICQ is associated with the gain. You increase your ICQ, your gain is going to improve. So if you increase your gain, your input impedance will suffer, okay. So that point you should remember, okay. If you because increasing ICQ means you are basically increasing your GM. That means you are basically increasing your gain, okay. So in other words, if you increase your gain, your R-pi is going to decrease. That is, the input impedance is going to decrease, okay. That is not good actually, because we want input impedance should be as high as possible, okay, for this kind of voltage amplifier circuit. But if you increase the gain, okay, your input impedance is going to decrease. What about the output impedance? For you remember, for output to find output impedance, your input side needs to be shorted because there was a voltage supply before that that you have to short it out, and this is basically your RC, and you can connect a voltage source here. Okay, uh, so that will give you so you can find out again the output resistance, okay, or output impedance associated with this circuit. Okay, that is nothing but RC, because you see this is this V pi is shorted, because you see there is a ground here, there is a ground here. This is shorted, means your GM V pi is also not there. Okay, so that means your uh, that means uh, your output resistance is nothing but RC. Okay, so if you keep your if you increase your RC, okay, if you increase your RC, your R out going to increase. Okay, uh, sorry, your gain is also going to increase. Okay, however, we don't want R out to increase, right? We don't want R out to increase. What will happen if we keep our RC fixed and increase the voltage gain? In that case, if we, so this is another point you should be noted. And third point you should note is, if RC is fixed, okay, your whereas you increase your gain, if you increase voltage gain, voltage gain if you increase, I think I should go to the next slide. So if we increase voltage gain,
so can you please go back to the previous slide?
yeah, yes. So what I actually point out is, if you increase the gain, okay, your input resistance or input impedance will decrease. Okay, that is not good, but that is the relation is showing that. And in case of output impedance, it is RC is the output impedance. If we just for the time being don't bother about our R naught, that is the resistance, output resistance associated with the early voltage, okay, or early effect, then R out is basically RC, and if you increase your RC, your gain will improve, because gain is GMRC, okay, magnitude of gain, but that will increase R out. Here also increasing R out is not good, because we want R out as small as possible and R in as large as possible. Okay, so that is what I want to just jot down in a single line, that if we keep our RC fixed, okay, whereas so that will keep R out fixed. Okay, however, if we increase voltage gain, that we can do only by increasing ICQ, because we are fixing RC. In this situation, your input impedance will suffer. Okay, we can simplify that argument little bit further, and say that we know AV is equal to minus GMRC. Okay, that is nothing but minus beta over R pi RC. Okay, so that will give us minus beta R out over RE. Okay, so because your R pi is R in and your RC, if we fix our if we fix our input output impedance, input output impedance is already if it is AC are already specified, okay, in that case gain is automatically set, okay, because you see it is gain is automatically set, okay, because you see your gain is R out over R in, okay. If you consider your, if you take into account your early voltage effect, okay, considering early voltage effect, then okay, then you have to consider R naught. In that case, obviously the gain will be minus GM RC parallel R naught, right? Because R naught is coming to the parallel of that RC, okay. You can draw the circuit and figure it out. You can draw the circuit and figure it out, because this is your GM V pi, okay, and your R naught is will come here, okay, because of this early voltage, because you remember R naught should be in parallel, because R naught is the resistance which is basically slanted that ICE VCE curve, right? You remember it will not be flat because of that R naught. So R naught will come in parallel to that GM V pi, and there is RC here, okay. So if you then find out the gain, you will see that R naught will parallel to RC will come, and also in the output resistance also. So in this case gain will be minus GM R naught parallel RC, and R out will be R naught parallel RC, okay, whereas your R in will remain intact, okay, that is obvious. Now hypothetically, if RC is infinite, okay, say hypothetically RC, there is no RC, okay, I haven't connected any load at the RC, then we can say that gain is basically minus GM R naught. That is often known as intrinsic gain of your BJT, okay. So that's like intrinsic gain, okay. If we assume that we haven't connected any RC, then intrinsic gain of the BJT is GM R naught, okay. You can replace R naught with VA over IC, okay, and GM we know that IC over VT, okay. That suggests your AV in that case will be mod AV in that case will be VA over VT. So your intrinsic gain obviously doesn't depends on doesn't depends on your bias current, you see, okay. It doesn't depends on your is independent of your bias current, okay. Now we would like to discuss a bit more. If we assume that so the one particular point I mentioned in the last slide, okay, you see I think one slide before, you see that that if we increase gain, your R pi deteriorates, I mean your input resistance deteriorates, and also if you increase your gain by virtue of increasing RC, your R out will deteriorate, okay. So how to improve this situation? Okay, we can improve this situation by changing our design a bit, which is known as emitter degeneration. Okay, this is also we have come across before when we discuss our voltage divider biasing, but we haven't discussed this particular aspect of emitter degeneration, where your input, we will see that your input impedance will improve if we have like emitter degeneration. What is emitter degeneration? That is like we don't connect emitter directly to the ground. Okay, so this is your V in and this is your RC VCC. We have your V out here, and instead of directly connecting to this to ground, we have RE. So this is this particular design is known as, sorry, so this particular design is known as common emitter stage with emitter degeneration. Okay, now if we have this RE, we have seen its effect when we are discussing biasing, but let's discuss it even further, because it will give you new insights as far as the input output resistance and gain of the circuit is concerned and all that. Okay, we have seen when we are discussing biasing, we have seen this RE gives more stability in the biasing, because it acts as a negative feedback and improve or reduce the effect of VBE, because by having a certain voltage drop across RE, right? So that reduces the VBE, and that can happen, that can improve your situation while thermal runaway and all that. Okay, so let's discuss this effect in case of common emitter amplifier. Okay, you see, if we increase your V in by delta V, you see, if RE equal to 0, okay, then if you increase delta V in V in, your collector current going to increase, going to change by delta V. Okay, collector current going to change by GM delta V, right? But if you have like RE in between that emitter and ground, then this delta V will not entirely change your VBE. Okay, some part of this delta V will be across this RE as well. Okay, so your so that implies your GM delta V current change will be less, because this delta V is not changing your VBE. Some part of the delta V will be absorbed by this RE emitter resistance. Okay, so you see your corresponding base current. Okay, this corresponding base current, your corresponding collector current will not change, will not be equal to GM delta V. Change in delta IC will not be same as GM delta V that in the previous case, because some part of delta V will be absorbed by RE. And similarly, GM delta V over beta, that's basically the base current change, will be less, because some part of the delta V is absorbed by RE. Okay, so if we try to find out the gain associated with such circuit where we have this emitter degeneration situation, we can draw the small signal equivalent circuit again. Okay, you see, this is your RE, this is again GM V pi, and I am as usual for the time being neglecting any other bias resistance, and also we are basically neglecting R0, that is because of the comes into play because of early voltage. Those things we can consider later on, but let's concentrate on only on these few factors. Okay, and you see we can write as usual. This is very straightforward. We can write okay, gm v pi is equal to minus v out over rc, and also we can write vre, that is the voltage drop across re, that can be written, this is my current, one current, so two currents are going to re, you see, going through this re, so we can write v pi over r pi plus gm v pi multiplied by re, that is the voltage drop across re. Okay, and we know we know that v in will be equal to v pi plus vre, right? That is obvious because this is through v in, sorry, so through v in this is basically grounded, right, through this input signal. So we can say that v in, one part of v in will drop across r pi and another part will drop across re, right? So we can find out v in plus vre, and ultimately what we will get if you replace, if you put the above equations. Okay, in this, and ultimately you can find out v out over v in, okay, is equal to minus gmrc over 1 plus 1 by r pi plus gm into re. So that's the final expression for the gain, okay, of such a circuit, where we have introduced this re factor. Now you can simplify this expression bit further, because you see we know that beta is equal to gm into r pi. Okay, we know that, so we can neglect this 1 by r pi terms, because okay, because usually beta much greater than 1, which implies gm much greater than 1 by 1 over r pi. Okay, so if we neglect that particular bit, then we will end up with gmrc by 1 plus gm re. Okay, so we can sorry, let me add few more slides. Okay, so give me a second. The reason I am using these slides, probably this will help in because you said your the quality of the of those PNG files or the file I have uploaded yesterday is not good. I have seen that, so I thought that let's write it in PPT, and this we can then upload these PPTs. Okay, so what I yeah, so so what we so this is expression AV nearly equal to minus GMRC over 1 plus GMRE, where you see our in the so far whatever we have discussed, if we don't have if RE equal to 0, Okay, sorry, if R equal to uh, if R equal to 0, then if R equal to 0, then gain was minus GMRC. Okay, and if RE not equal to 0, then gain is minus GMRC over 1 plus GMRE. Okay, so you see your gain falls by a factor of this. Okay, so your gain is less if you have RE, your gain is less. Okay, by this 1 plus GMRE factor. Okay, you can um, um, we can discuss a bit more about this particular relation. This relation is extremely important. We can divide your numerator and denominator by GM. Okay, and that will give you okay, this is a very important relation, okay, which I hope you will be able to remember very easily. The way you remember this, that the gain of this degenerate common emitter stage is equal to the load resistance seen from collector. Okay, load resistance, if we just neglect our early voltage, this RC is the load resistance seen from collector. Okay, and divided by the 1 by GM plus the total resistance placed in series with that of emitter. You remember when we were discussing our impedances looking from different side. Okay, if we ground AC and DC ground, if there is a resistor RC, and if we don't bother about R naught, then the resistance looking from this collector side will be RC, right? Similarly, you remember when we discuss about your resistance looking from emitter side, it was like 1 by GM. Now if you look at this formula, you see the gain is depends on RC. Okay, the gain is of this degenerate semiconductor is equal to the load resistance seen from this collectors to ground. Okay, divided by, you see it is 1 by GM plus the resistance you have added in this emitter. So it is very easy to remember. Okay, so RC associated with RC is basically associated with the collector. Okay, so the resistance you look from the collector side, collector to ground, the gain, divided by, if you look from the emitter side, that is 1 by GM is the impedance, plus you have added your degenerate resistance RE. Okay, so that's a very important observation, that if you divide these two resistances, you will basically get the gain. Okay, but you see the important point is your gain is going to fall. Okay, if you add your RE. We will discuss in the next class that incorporating RE will improve your input input impedance or input resistance. Okay, so that is one advantage of including RE. Okay, this we will see in the next class, and also we will see that this incorporating RE is not changing your output R out, no change. Okay, so that is also important. R out remains the same, and that is RC or RC parallel R naught, if we take into account that early resistance associated with early voltage. Okay, but important point is it will improve input impedance. Okay, but this gain thing we will see in the next class. We will be able to improve even in the gain side as well. How we can improve the gain side? Just I give you a hint. If we short circuit this RE, okay, you see, if we short circuit this RE, or this RE is AC ground, then your input impedance is going to improve. Okay, so that we will discuss in the next class. So this is your V in, this is the RC, and this is the VCC. Now there is RE here. That RE, what it is giving, it is giving more stability in the biasing circuit, and it also improves your input impedance. So what you can do, you can bypass this this resistor or a part of this resistor, so that when it is when the DC signal is there, it can see the whole RE, okay, but when the AC signal is there, it will see a part of RE or no RE at all. Okay, so that will improve your gain. Okay, while you will be able to bias the circuit more perfectly. Okay, so here I am stopping today. We will discuss this in more detail in the next class. Okay, so thank you very much. If you have any queries, please raise your hand and we can discuss those.